Welcome back to the Deep Dive. We have a fascinating stack of papers today, and I'll be honest, when I first saw the title on these Bayesian networks and sampling, I thought, oh boy, this is going to be a very dry hour of math.
I can see that. It doesn't exactly scream excitement.
It really doesn't. But then I started reading, and you see these notes about predicting the future, diagnosing diseases, and I realized this is really about how we handle, uncertainty.
It absolutely is. It's the core problem, right?
Yeah.
How do you know what's going on when you only have a few pieces of the puzzle?
Exactly. And we're diving into this idea of inference. We've got this model of the world, this whole web of causes and effects, and we want to ask it a question.
And the classic example they always use, the hello world of this field, is the famous wet grass model.
The wet grass model.
Right.
It seems so simple on the page. You got 4 little circles. Cloudy is at the top.
Mm-hmm.
And if it's cloudy, that affects whether the sprinkler is on and also whether it rains.
And then both of those things, the sprinkler and the rain, they affect the final variable.
Whether the grass is wet.
Exactly. A nice, clean causal chain.
But here's the kicker, and this is where the notes get stressful almost immediately.
Yeah.
Drawing the picture is easy.
Oh, yeah.
Asking a question like, okay, I see the grass is wet. What are the odds it's cloudy? That turns out to be a mathematical nightmare.
It is, and that's the central tension we're talking about today. That's inference.
Yeah.
You have the evidence, the wet grass, and you want to infer the cause. And if you try to calculate that percentage perfectly, what we call exact inference, you just hit a wall.
The notes mention a couple methods for this, enumeration and variable elimination. They sound technical, but then there's this big warning label next to them.
Exponential complexity.
Which is a polite way of saying what, exactly?
It's the polite way of saying, don't even try it.
Impossible.
For any real-world system, yeah, practically impossible. I mean, look, for our little 4-variable weather model, sure, a computer can do the exact math instantly. But imagine a medical diagnosis network. Maybe 500 symptoms, 300 diseases, all interconnected. Every time you add a variable, the amount of work to calculate the exact probability, it explodes.
It just scales up so fast that even a supercomputer would choke.
Right. If you tried to do exact inference on a really complex AI model, the heat death of the universe would probably get here before your answer did.
So we're stuck. We build this amazing model to understand the world, but the math is too hard to actually use it.
And that is where we pivot to the real hero of today's deep dive.
Sampling.
Sampling, or a more technical term, approximate inference.
I love that. It's basically the universe saying, look, I can't give you the exact answer, but I can give you a really, really good guess.
That is the perfect way to put it. Think about it like this. You want to know if the Lakers are going to win their game tonight.
Okay.
You could try to calculate the physics of every single atom in the basketball, the air resistance, the biomechanics of every player.
That's the exact inference route, the impossible one.
Exactly. Or you could just fire up a really good basketball video game and tell the computer to simulate the match 10,000 times.
And if the Lakers win, say, 8,000 of those simulated games.
Then you say, there's about an 80% chance they win. You didn't solve the math, you just ran a simulation and counted what happened. That's sampling.
Okay, that makes total sense. We're trading perfection for speed. But let's get into the how. Because running a simulation sounds simple, but how does a computer actually do that? The first method in our stack here is prior sampling.
Prior sampling is the absolute baseline, the simplest way to do it. And to get your head around it, you have to look at the engine under the hood.
The random number generator.
A random number generator, yeah. That random function in your code that just spits out a number between 0 and 1.
Like a weird digital die.
A very weird 1,000-sided die. So let's go back to our weather network. We start at the top, at the parent node, cloudy. Our data says there's a 50% chance of clouds.
So the computer rolls its die.
It rolls its die. If the number is between 0 and 0.5, the simulation decides, okay, in this imaginary world, it is cloudy. If it's over 0.5, not cloudy.
Simple enough. But what's next? Because the next thing in the chain is the sprinkler, and, well, the sprinkler's behavior depends on whether it's cloudy.
Precisely. This is the key. You always walk the network top down, parents to children. So let's say our simulation just decided it is cloudy. Now we move to the sprinkler node.
And most people don't turn on their sprinklers when it's cloudy.
Right. So maybe the probability of the sprinkler being on is usually, say, 50%, but given that it's cloudy, it drops to just 10%. The computer looks that up, it sees cloudy is true, so it uses the special probability table for that case.
And it rolls the die again.
It rolls again. But now it only says the sprinkler's on if that random number is really low, between 0 and 0.1.
Oh, I see. So the decision we made at the top constrains the possibilities as we go down.
It ripples down the chain, exactly. And then you do the same thing for rain. If it's cloudy, rain is likely. So you roll for rain with a high probability. And finally, you get to wet grass. And you look at what happened with rain and sprinkler, and you roll one last time.
And at the end of all that, you have one complete story.
One complete sample. Maybe this one is cloudy, sprinkler off, raining, grass wet.
And then we just do that again.
1,000 times, 1,000,000 times, as many as you can. And then, if you want to know the probability that it rained, you just count. In how many of our million stories did it rain?
It seems, I don't know, almost too straightforward. If this works so well, why are there 3 more sampling methods in these notes?
Because prior sampling has one gigantic flaw. It totally ignores the one thing we almost always have in the real world.
Evidence.
Evidence, yeah. We rarely start from a blank slate. Usually we look out the window, we see the grass is wet, and we want to know why.
So we know the ending. We have a fixed piece of the puzzle.
Right. The technical term is we've clamped a variable. We know for a fact that the grass is wet.
But prior sampling doesn't care. It just starts at the top and guesses blindly.
It's flying blind. So you want to know, given the sprinkler is on, what's the chance it's cloudy? You run your prior sampling, it flips a coin for cloudy, then it moves on and flips a coin for sprinkler. And maybe in this run, it decides the sprinkler is off.
But I know it's on.
The simulation doesn't. It just generated a world that contradicts your reality.
So that sample is completely useless to me.
Totally useless.
Well, that just seems like a massive waste of computing power. The computer's just babbling about scenarios I know are false.
Which brings us, very naturally, to method number 2, rejection sampling.
Rejection sampling. Sounds a bit harsh.
It is harsh. You're basically swiping left on your data. You run the prior sampling process exactly like we just described. But at the very end, you add one more step.
You check it against the evidence.
You check it. You ask, in the world I just simulated, is the sprinkler on? And if the answer is no, you take that entire sample, all that work.
And you throw it in the trash.
You throw it in the trash. You reject it.
Wow. Okay, so you only keep the timelines that actually match what you observed.
Correct. The source quote here is very direct. Ignore reject samples which don't have S plus S. And then you do your counting just on the survivors.
And does that actually work mathematically?
It does, surprisingly. It's what we call consistent, which is the stats term for if you run it forever, it'll eventually give you the right answer. But think about how inefficient this is.
Yeah, I can see the problem coming. What if my evidence is something really, really rare?
You've nailed it.
Like, say I'm a doctor, I'm trying to diagnose a disease that only affects 1 in a million people, and my evidence is this patient has the disease.
Okay, so you start your simulation. It starts with the general population. It rolls the die for has disease. It's a 1 in a million chance.
So the die is almost always going to say healthy.
Almost always. And every time it generates a healthy patient.
I have to reject it because my patient is sick.
You reject it, run it again, healthy, reject.
You will have to run that simulation about 1 million times just to get one single sample that matches your evidence.
That is just unbelievably wasteful. It's like trying to find a needle in a haystack by just burning the whole haystack down and hoping the needle survives.
That's a great analogy. Rejection sampling completely crashes and burns when the evidence is unlikely. And in the real world, that's what we care about. Security threats, rare diseases, market crashes. It's always the unlikely stuff.
So we need a way to, I don't know, force the simulation to cooperate, to tell the computer, look, I don't care what the dice say, the patient is sick, just start from there.
Exactly, we need to cheat. And that brings us to our third method, likelihood weighting.
Likelihood weighting. The name sounds promising.
So here's the trick. You start your simulation just like before. But whenever you get to a variable that is part of your evidence, you don't roll the die.
You just force it to be the value you observed. You just force it. If your evidence is sprinkler is on, when the simulation gets to the sprinkler node, you just set it to on, period, 100% of the time.
Okay, that solves the waste problem right there. Every single sample I generate is now guaranteed to match my evidence. I'm not throwing anything away.
True. But you can't just break the laws of probability like that and not pay a price. You've created a a biased world. You forced the sprinkler on even if it was a cloudy day when it should have been off.
Right. I've skewed the data.
So to fix the math, we give each sample a weight. You can think of it like a credibility score.
How was that calculated?
As you go down the network, whenever you force an evidence variable, you ask the question, what was the probability of this actually happening naturally, given the parents?
Okay, so if it's a sunny day and I force the sprinkler on, well, that's pretty likely. People water their grass when it's sunny.
Right. Maybe that probability was 0.9. So you give that sample a weight of 0.9. It's a heavy sample. It counts for a lot in the final tally.
But what if it was raining in the simulation and I still forced the sprinkler on?
Well, who waters their grass in the rain? That's super unlikely. Maybe a 1% chance, a probability of 0.01.
So I still keep that sample.
You still keep it, but you give it a tiny weight of 0.01. It's a feather light sample. It barely registers.
So at the end, instead of just counting the samples, you sum up their weights. The plausible scenarios count a lot, and the weird ones I forced barely count at all.
You got it. It mathematically corrects for the fact that you cheated.
That sounds kind of perfect. It's fast. There's no waste. Why isn't this the final answer?
Because of the direction of the arrows. Remember, all these methods so far, they walk top down, parents to children.
Okay.
Likelihood, weighting is great when your evidence is at the bottom or downstream, but it has a huge blind spot when the evidence needs to influence what happened upstream in the past.
I think I need an analogy for that one.
Okay, imagine your evidence is at the end of a maze. Likelihood, weighting is like trying to solve the maze by starting at the beginning, picking paths randomly, and then if you happen to hit a dead end, you just magically teleport to the end and pretend you meant to go there all along.
You're not actually using the goal to guide your choices.
Not at all. Let's go back to the weather. Our evidence is the sprinkler is on, and we want to know if it's cloudy. The simulation starts at cloudy. It has no idea about the sprinkler yet. It has to guess.
So it flips a coin. Let's say it guesses cloudy.
It picks cloudy, then it moves down to the sprinkler. We force the sprinkler on, but wait. If it's cloudy, the probability of the sprinkler being on is tiny.
So the sample gets a really low weight.
A catastrophically low weight. The simulation blindly made a bad choice upstream picking cloudy that made the downstream evidence incredibly unlikely.
I see. It's stumbling in the dark. It keeps creating these parent scenarios that make the child evidence almost impossible, so you just end up with millions of samples that all have these microscopic weights.
Yeah. Exactly. You're not throwing them in the trash like rejection sampling, but you might as well be. A weight of 0.000001 isn't very useful.
Okay, let's recap where we are. Prior sampling is too random, rejection sampling is way too wasteful, and likelihood weighting is like driving blindfolded. It can't use the evidence to inform its earlier guesses.
We need a method that lets information flow in all directions, from the past to the future and from the future back to the past. We need to stop walking in a straight line.
And that brings us to the final boss of these nodes. Gibbs sampling.
Gibbs sampling. This is a type of MCMC, or Markov chain Monte Carlo. It is the heavy hitter.
So how does this one work? It must be completely different.
It is a totally different philosophy. The other methods build a brand new world from scratch every single time. Gibbs sampling starts with one, maybe totally broken state of the world, and just sort of nudges it.
It nudges it.
It fixes it one piece at a time. Here's the process. First, you lock in your evidence. Let's say grass is wet. That value is frozen. It never changes. Then, for all the other variables, cloudy, rain, sprinkler, you just assign them random starting values, complete guesses.
So we start with a potentially nonsense world, like the grass is wet, but it didn't rain and the sprinkler is off.
A completely impossible world. But then the magic starts. You pick just one of the non-evidence variables to update, let's say rain.
Okay, just rain.
And you look at its immediate neighbors, its parents, cloudy, and its children, wet grass, and you ask a new question. Given the current state of my neighbors, what should I be?
Well, if the grass is wet, the math would strongly suggest it probably rained.
Exactly. So you resample the rain variable based only on its neighbors. It probably flips to true. Now your world is a little bit more consistent.
And then you move to the next one.
You move to the next one, say sprinkler. You ask, okay, given it's cloudy and we just decided it's raining, should the sprinkler be on?
Probably not, so it flips to off.
And you just keep cycling through the variables. Pick one, look at its friends, update it. Pick another, look at its friends, update it. Over and over. It's like algorithmic peer pressure.
That is the perfect analogy. It is exactly peer pressure. Each variable looks at its immediate social circle and says, oh, what are you all doing? Okay, I'll adjust to fit in better.
And this actually converges on the right answer.
It does. As you keep cycling through thousands of times, the overall state of the world wanders out of those impossible configurations and starts spending most of its time in the most probable, most consistent ones.
The notes have a great name for that immediate social circle.
The Markov blanket.
It sounds like a cozy product you buy online.
It does, but it's a really powerful technical idea. It means to update any one variable, you don't need to look at the whole giant scary network. You only need to look at its parents, its children, and its children's other parents. That's its blanket.
Which makes each little step really fast.
Super fast. And because you're looking at children as well as parents, information flows in all directions. The evidence that the grass is wet at the bottom puts pressure on the rain variable in the middle, which in turn puts pressure on the cloudy variable at the top. It solves the blindfold problem. The evidence finally gets to influence the causes.
Exactly. It finds a coherent story that explains everything you've seen, no matter where it is in the network.
Wow. Okay, so we've really been on a journey. We started with exact math, which was just too hard. Then prior sampling, which was just blind guessing.
Rejection sampling. Guessing, and then throwing most of it away.
Likelihood, waiting. Forcing the guess, but struggling with the past.
And then finally, Gibbs sampling. The peer pressure method that lets the truth ripple through the whole system.
It's this incredible progression from, trading perfect for fast and then trading simple for smart.
That's a great summary.
And, as we wrap this up, something strikes me about this. We're talking about how AI systems make predictions. But listening to you explain Gibbs sampling, this idea of constantly iteratively updating your beliefs based on your immediate surroundings.
It sounds kind of familiar, doesn't it?
That sounds like it.
There's a very compelling theory in cognitive science that the human brain is fundamentally a massive Gibbs sampler.
Wait, really? We're not doing algebra in our heads.
Think about it. When you catch a baseball or you try to figure out if someone's angry with you from their expression, you are not solving a massive probability equation. Your brain doesn't have that kind of raw computing power.
I certainly don't.
What you're probably doing is running these lightning-fast internal simulations. You clamp the evidence, okay, his eyebrows are furrowed, you run a few quick samples, you subconsciously reject the unlikely ones, maybe he just ate a sour lemon, and you settle on the most probable state, he's probably mad at me.
So we're basically biological prediction machines running on approximate inference.
We are walking, talking Monte Carlo simulations. We traded perfection for speed millions of years ago because when a lion is running at you, getting a good enough answer right now is a lot better than getting a perfect answer 10 minutes too late.
That is a wild thought to leave us with. The next time you have a gut feeling about something, just remember, that might just be your internal Gibbs sampler finally converging on an answer.
It's always fun to see how the math ends up mirroring the mind.
Thank you so much for guiding us through this today.
My pleasure.
And thank you for listening. We'll see you on the next Deep Dive.